Hi everyone and welcome to this lecture. As you can see that today we are going to discuss about series solution near an ordinary point, that is a regular point for a differential equation. And as an example we have taken the second order equation, and if you just look at this equation you can easily see that this p of t that we saw earlier, that is in the standard form or the most general form, p of t is just 1, q of t is 0 because there is no such term of y prime, that is the first derivative of y, and r of t is 1 as well. These are just numbers. So from here you can easily verify that t is equals to 0 is an ordinary point or a regular point. So t is equals to 0 is an ordinary point, and we want a solution around this t is equals to 0. Okay, so let's proceed. So what the first step in series solution is that the solution that you want, you have to write it. Let's just mention this t for completeness. The solution you want have to come in the form of a power series. So the most general form of this power series will be just something like this: t minus t naught to the power n, right? And here this t naught is just 0 because we want a solution around t is equals to 0. So in our case this will simplify to n equals to 0, infinity, an, and t to the power n. And now the second step lies in the fact that you have to do some differentiation. That is, you have to find this y double prime. Obviously if there were a y prime term you have to find that as well, and you have to put this series into the differential equation. So first let's try to find this y double prime. That is, you are taking the second derivative with respect to t of this series, and obviously you know that derivative is a linear operator, so it will cross past this summation symbol, and differentiating twice will give you simply n into n minus 1 a of n, since a is just a constant, and you'll have tn minus 2, right? And now what you're going to do is that we are going to substitute all these things into the differential equation. So if you do that, you will have n equals to 0 to infinity, n into n minus 1 a of n t to the power n minus 2 plus sum over n equals to 0 to infinity a of n t of n equals to 0. And now you can see that if you start from n equals to 0, these terms will yield t to the power negative something. That is, if you put n equals to 0, then it will give you t inverse 2. If you take n equals to 1, it will give you t to the power minus 1, and so on. But if you start from n equals to 2, you can see that it starts with t to the power 0, then t to the power 1, and so on. So that's one way to see it, and a shortcut way to understand that what you need to do right now is that you need to factor out something like this t to the power n, and then you to do that you have to do some manipulations, and we're going to see that. But the logical reason is that we don't want any terms that has some t to the power negative something, because if you have t to the power negative, let's say 2, this means at this is just 1 upon t squared. So what will happen is that 0 won't be a regular point anymore, it would rather be a singular point. So that's the logic. But another way to just keep a mnemonic is that you just need to factor out this t to the power n. So we need to modify this term. We need to modify this. So how can we modify this so that we can factor out at something like t to the power n, right? Obviously this summation index, that is n, is a dummy variable. That's the first trick. N is a dummy variable, or the first important thing to realize over here is that n is a dummy variable. And if you recall, these dummy variables can take any form they want. Instead of n, you could have written m, you could have written x, it doesn't matter. They all mean the same thing because it's getting summed out. And since for n equals to 0, 1 and 0 and 1 you are getting some negative power, what you want to do is that take this power that's causing the trouble, this n minus 2, and replace this thing with m, right? And if you do that, your summation will now not be from n equals to 0 to infinity, rather it will transform into m plus 2, or because from here you can see that m plus 2 equals to n, so let me just write it down for your convenience. And when n is 0, this means m equals to minus 2, right? So this will start from m equals to minus 2, and when n is infinity, m is also infinity, so this will simply be from m equals to minus 2 to infinity, and n is equals to just m plus 2. So if you put, that means if you use this replacement, n minus 2 equals to m, what we now will have is something like this. So let me just write down the terms. This will be m equals to minus 2 to infinity. You will have a m plus 2 over here. You will have a m plus 1 over here. Instead of a of m, you will get a m plus 2. And now you have t to the power m. But then again, this m is what? This is a dummy variable, right? So m is dummy. So now what you're going to do? To keep things convenient, you're just going to replace m equals to n again. This might seem a bit absurd, but it's perfectly logical because m is a dummy variable. It can take any face it wants. So you have to write now is that minus 2 to infinity, n plus 2, n plus 1, a n plus 2, t to the power n. And finally, you are going to replace this thing over here into the series solution that you wrote, that means in this part. So let us write down the whole thing using this. So it will start from n equals to minus 2 to infinity, n plus 2, n plus 1, a of n plus 2, t to the power n, plus sum over n equals to 0 to infinity, a of n, t to the power n. Now you can see that we can easily factor out t of n. Obviously there is a 0 on the right hand side, but now the problem is this summation starts from minus 2 and this summation starts from 0. So what you do? You just take the terms, that is this minus 2, minus 1, 0, 1, 2, 3, right? These are the terms for this. So all I need to do, I need to evaluate this summation over here for minus 2 and minus 1. But if you notice that it has some n plus 2 over here and n plus 1 over here. So when n is equals to minus 2, this part goes to 0. And when n equals to minus 1, this part goes to 0. That means these two won't contribute anything. So again, the non-zero contributions will come from starting n equals to 0. So finally you write n equals to 0 to infinity, a n plus 2, n plus 1, n plus 2, t to the power n, sum over, okay, let's write t to the power n outside so that in one line we are also done with this factoring thing. And obviously I won't write the summation because now all the summations will be the same. So yeah, an, and you write t to the power n equals to 0. And we demand t to the power n not to be 0. We demand t to the power n not 0. Why? Because if t to the power n is 0, for any n, this is just a trivial solution. And we don't want that, because if t to the power n is 0, then our y is 0. This is a trivial solution. We don't need it. We want the non-trivial solution. So by demanding t to the power n is not 0, we get sum over n equals to 0 to infinity. Okay, I think this is a bit, yeah, this is more convenient. So let me write this thing again. We get sum over n equals to 0 to infinity, and here we have something like n plus 2, n plus 1, a n plus 2 plus a n equals to 0, right? That is the thing we get, and this will be true if and only if all the terms, that is, this is a summation, right? And all the summations are contributing, the net contribution of this sum is 0, but all of these are positive numbers, so that's why all the individual terms, they should cancel each other out. So by demanding n plus 1, n plus 2, a of n plus 2 plus a of n equals to 0, we finally end up having a recursion relation, and that is nothing but a n plus 2 is equals to minus a n divided by n plus 1 n plus 2, right? This is a recursion relation, and when you are done finding this recursion relation, you are technically done. All you need to do is that you need to find some terms and you need to add them up to find your solution. So let's check some cases and evaluate some terms. So what we're going to do is that we're going to start from n equals to 0 because the summation was like that. Okay, so when n equals to 0, we can see that the left hand side becomes a2 and the right hand side becomes a0, 1 and 2, and this can be written as minus a0 2 factorial. Okay, obviously a0 is what? Something we don't know, but that doesn't matter, and you will see in a few minutes why. So when you go for n equals to 1, you will see that you will have a3 over here, and this will be minus a, what was that? I'm sorry, I forgot. Yeah, that was a of n. So this is just a of 1, and you'll have 2 and 3. So this is 2, 3. Obviously there's a 1 over here, and this can be written as a 1 divided by 3 factorial. Similarly, for n equals to 2, you will have a4 minus a2 divided by 2 plus 1 is 3 and 2 plus 2 is 4, something like this, right? But if you notice that a2 is something already sitting over here, and this is coming in terms of a0 or a underscore 0. So this is just, there's a minus over here and a minus over there. They will give you a net plus sign, and you will have a0, and you will have 2 factorial times 3 times 4. This is just a0 by 4 factorial. And similarly, if you go for n equals to 3, you will have a of 5 over here, and this will come in terms of a of 3, and in the denominator you will have 4 and 5. However, a3 is already written in terms of a1, so you can use that to your advantage, and finally you will have this a plus over here, and you will have a1 3 factorial times 4 into 5, that is just a1 by 5 factorial, and so on. So you can see that there is actually 2 summations in this sum. One of them is coming from n equals to even, and one of them is coming from n equals to odd. And if you do the even part, that is, you start from n equals to 0, then you have n2, n3. This just decouples into 2 sum. The whole sum decouples into 2 summations. So the even part, where n is equals to even, this gives you something like whenever this n equals to 0, this gives you, that is, n is equals to 0, n is equals to 2, n is equals to 4, and all that. This gives you the following. Obviously I need to see the terms again, so let me zoom out a bit. a factorial, sorry, a0 by 2 factorial, a0 by, yeah, the second one is minus, right? a0 by 4 factorial. Yeah, the first one was minus. And if you go for n equals to 4, you will find another minus something like this, and dot 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 dot. And for n equals to odd, you will have this minus a1. Was it minus a1? Yes. And you will have a 3 factorial thing. You will have, then n equals to 3, you will have a plus a1 5 factorial thing. Then there will be another minus and another plus. And this series are nothing but the sines and the cosines. Because if you simplify these terms over here, so let's not write the summation symbols anymore. Just factor out this a0, minus 1/2 plus 1 by 4 factorial. So obviously there will be a factorial, sorry for that. Minus 1 by 6 factorial, because this is even. So the hard work lies in recognizing the series and evaluating the terms. And these are just series of sines and cosines, because this is our this is the recursion relation, right? And finally we have to write this in the format that we saw earlier, that is from n equals to 0 to infinity, and there is this t to the power n, and these are our, oops, sorry about that. And these terms over here, these guys, these are just our n's. These are our n's, that means the coefficients. So lastly, you just put all of them together and you will have this thing, y of t as some parameter that is a constant, and you will have, let's say, the first term, you can see that this will just be a0, that is this a0 minus 1/2, so 2 like this, and there will be the second term that is for n equals to 2, so that will be, sorry, I'm very sorry about that, this is for n equals to 0, and there will be this n equals to 1 term where you'll have a a1 like 3 factorial and all that, t to t square and dot 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 dot. So finally you can factor them out, a0 like this, and you can write cos theta and a1 sin theta, something like this. And it's not always possible to recognize the series. In this case we were lucky, so this is our solution. And in fact you can be even more formal, since this is a second order equation. You expect the solutions to be of the form c1y1 of t, c2y2 of t, where this y1 and y2 is just, this is your y1 and this is your y2. So this will be it for today, and most of the time we actually don't think much about this regular point solutions. Rather we will try to see how the solutions of the differential equation look about their singular points. So this will be it for today, and from the next video we are going to see how we can construct a series solution for singular points. Thank you.